So now we're going to look at getting equations from truth tables. And this is going to be a little bit more involved than what we had before. So what we had just done is we went the other way around. We took equations and we figured out what the truth tables were. But how about doing it the reverse? So if I give you a truth table, can you figure out what the logic equations are? Now there's a good question. Why would you want to do this? Why is this direction more interesting than the other direction? So let's take a look at an example. Here's a truth table for a function. And I want to ask you, does this function look familiar? Well, it's sort of hard to just look at this function and figure out what it is. How about if I replace s and c with sum and carry? If I now tell you that this is a function which has two inputs, a and b, and two outputs, sum and carry, does this function look familiar? And it should. This is a truth table that defines the behavior of a one-bit adder. We spent a lot of time looking at arithmetic, and here's exactly what you expect. So if I go in here, I add 0 and 0, I have 0 output and no carry. If I add 1 and 1, I have 0 output and a carry of 1. So this is the truth table that defines an adder. So why do we want to be able to go from truth tables to equations? Because we want to build logic from functional definitions. We want to define how the logic behaves by its truth table and then figure out how to build it using gates. So let's take a look at some examples here. Let's build a half adder, and we'll start out looking at the sum output. So before I get started here, what is a half adder? And why would we only build a half adder? Well, a half adder is an adder with no carry in. Remember, usually when you're adding, you add three things. You add a, b, and the carry in. A half adder has no carry in, so it's just a plus b and getting a sum and a carry out as a result. And why are we looking at this? Well, it's simpler than a full adder. Don't worry, you'll get to do the full adder later, but now we're just going to look at the half adder. So, to figure out how to build a half adder, let's start looking at one of the outputs. We'll start looking at just the s, or the sum output. So what logic function is this? Here we have our truth table, the inputs are a and b, and the output is s. Well, this may not be totally obvious, so let's start out a little more systematically. Let's find all the places where the sum output s is 1, and then we'll look at the inputs. So s is 1 here, and that's whenever these inputs are true. So sum is true whenever a is 1 but not b, or whenever b is 1 but not a. Do you recognize that logic function? This is one of the trickier ones. This is an XOR pattern. So if we look at the truth table for XOR, we see it's exactly this. Either A or B, but not both. It's an exclusive OR. So now we've figured out what the equation for S is. The sum of a half adder is A XOR B. Now let's do the same thing for the carry output. So here's our truth table for the carry output. A and B are inputs and C as our output. Can you figure out what logic function this is? Well, we'll go ahead and start, find all the places where C is 1 and circle them. So C is only 1 in one place, and that's the case where A and B are both 1. So this is a pretty easy gate to identify. This is an AND. When A and B are 1, then C is 1. Here's the truth table for the AND gate. So now we've identified that the carry out equation is C equals A and B. And this makes sense. We saw that we only have a carry out if we're adding 1 plus 1. Then we get to have an output of 1 in our carry because we've overflowed. So it makes sense that this is an AND here. So here's our complete half adder. We have two gates, one for the carry, and the carry is only true when A and B are true, so C equals A and B, and one for the sum, and sum is true when either A or B are true, but they're not both true, so this is XOR. And so here's the equation, here are the gates, and here's the truth table for a half adder.